Hello, everyone. I think it's time to start with the last talk of the seminar series 2024 in the fall semester. Welcome. It's good to see so many of you here. My name is Andreas Müller. I am one of the co-leads of the IDL at Design++. The IDL is the Immersive Design Lab. Maybe some of you already visited it. And Design++, just very briefly, is the Center for Augmented Design and Architecture, Engineering and Construction. And it has several goals on its schedule. And one of the goals is the knowledge transfer, which was basically also the initial idea of coming up with a seminar series like this one back then. And by now it also became a lecture for PhD students, which is very nice. And as I said, we are already at our last talk. If somebody missed the previous ones, we have a YouTube channel. You can rewatch all the talks, also from this semester and from the last semesters, actually. And with this, I would like to forward already to our next speaker, Brent Chamberlain from the Utah State University. And he was actually here for the last 6 months and working with Ulrike. So that's why we actually thought it would be a nice idea if she introduces you, since you worked so closely together. So,
thank you, Andy. My name is Ulrike Wissen. I'm the director of the large-scale virtualization and modeling lab, which is also part of Design++. And I have the honor to introduce to you Brent Chamberlain. So as you heard, he is professor at the Utah State University in landscape architecture and environmental planning. And he was an assistant professor at Kansas State University in the Department of Landscape Architecture and Regional and Community Planning, and did his postdoc at the University of British Columbia in Vancouver. And there he had joined appointments in the Institute for Resources, Environment and Sustainability, Computer Science, and the Faculty of Forestry. And during that time, he also went to the EAWAG, so it's not his first time working here in Switzerland. And Brent calls himself a computational environmental planner. And his research topics include geographical and land information science, artificial intelligence, design and spatial cognition, and cultural ecosystem services. And in particular, he focuses on visualization and spatial data science, developing techniques to analyze data, explain spatial phenomena between human and natural systems, and develop software to facilitate planning. The second focus is on applying and developing computational approaches toward planning and design problems, both practically and theoretically, including optimization, modeling, and AI approaches. And the third focus is on better understanding and explaining connections between humans and our natural world through psychological constructs. And this latter topic brought us together here at ETH. So I know Brent, or we know each other already for a very long time, because we are also visiting the same conference each year, the Digital Landscape Architecture Conference. And approximately 1.5 years ago, it was when Brent and I talked that it would be great if we combine his research on eye tracking in virtual realities with our 3D point cloud-based, really realistic landscapes in virtual reality. And we continued talking about this and thought it would be a nice idea to compare then perception in these virtual environments with the perceptions in the relating outdoor environment. And here is where Peter Kiefer from the GeoGaze lab here at De Baug from the chair of Martin Raubal, Geoinformation Engineering, came into play, because Peter and his team, they are really experts in eye tracking, not only in virtual or not not only indoors, but also in outdoor environments, and he has the facilities, the glasses to do that. And so we wrote together a proposal for the Swiss National Science Foundation to get the research visit of Brent funded. And this was approved more or less 1 year ago. And half a year later, Brent and his family arrived here in Zurich. And so we conducted our study. And this is a moment where I would like to thank a lot of you who are here today, which I remember participating in our study with. Without your help, we couldn't have conducted or collected this valuable data in such a short time. So thank you very much, and thank you for being here. Brent will now continue and present to you the first results of the study. So the floor is yours.
Excellent. Thank you very much. Yay. Thank you, everybody, for being here towards the end of this semester or term, whatever you refer to. I do appreciate an audience. It's quite nice. And also, thank you for those of you that participated in the study. We're quite excited to show at least the first pass of the data analysis that we've done with this. It's been a very short turnaround. I also would like to thank Design++ for hosting this and for the Plus department in supporting me coming here and the work with Ulrike. It really is an honor and quite a special experience in one's life to be able to have a sabbatical and go somewhere else and study and meet new people and learn new things. This is really an amazing opportunity to exchange ideas. So thank you very much. So this is how the title was supposed to look, VR, Vision 3D with some VR. I have a QR code here if you're interested to know more about what I do, and it'll show up at the end as well. So just to thank the team who has been working on this project. You know Ulrike, and Peter was also introduced. Also thanks to Chair Adrienne and Plus. But I have to also thank Laura for a lot of work in the point cloud development and carrying on a previous project. And one of my PhD students, David Evans, who some of you had an opportunity to meet while he was here for about a little over a week. So the project was funded by Swiss National Science Foundation, and I also received some funding from the Utah Agricultural Experiment Station to support some of this work. This slide is an inverse Gaussian transparency of what people looked at in the outdoor space for only part of this panorama. So the reasons we're interested in doing this work is because you create cool visualizations. But actually also for two primary reasons that are somewhat methodological. So landscape visualizations and also navigation and how we assess those. Landscape visualizations are used quite a lot in scenario planning and development, and also in scenery management, so environmental impact assessment, for instance. And in navigation, we're interested in how people wayfind, in particular, make decisions. This project focuses on the landscape visualization, the sort of scenery component of things, but the whole idea of understanding the mechanisms of what people are looking at and how that can make a difference in interpretations and perceptions is part of what this work is for. So this is an example of scenario visualization from Plus, from an EnergyScape project. So here you're all looking at different things, and I would like to know what you're looking at and the patterns of that observation, and in particular what you might be missing. Because this can play a role in how we might design and lay out different artifacts and develop the landscape. So at a theoretical level, I'm bringing in an image here from David Evans, who's been developing some concepts around how we go from these spatial objective data about what the environment is, things like where are trees and concrete and grass and these sorts of things that we typically get from remotely sensed imagery or other sorts of objectively collected data, all the way to how we evaluate that. So this is an example of scenario visualization from Plus, from an EnergyScape project. So here you're all looking at different things, and I would like to know what you're looking at and the patterns of that observation, and in particular what you might be missing. Because this can play a role in how we design and lay out different artifacts and develop the landscape. So at a theoretical level, I'm bringing in an image here from David Evans, who's been developing some concepts around how we go from these spatial objective data about what the environment is, things like where are trees and concrete and grass and these sorts of things that we typically get from remotely sensed imagery or other sorts of objectively collected data, all the way to how we evaluate that. And what we typically get are things like in the spatial data, that we try to transfer that to some sort of scene, a perspective view. And we can develop different metrics, like how much green we see in a particular space, or how much concrete we see in a particular space. And usually, we take those scenes and we might ask people, can you rate these, or can you give us some sort of feedback? And the process of that involves this viewing behavior where we look around and then we categorize that in some way through perception. And then we give some sort of statement of value, and that's our preference. The challenge is most of these studies do not have a good way of categorizing the actual viewing behavior, the mechanism that helps us understand what you're looking at in the scene data and what's happening in their perception. That's what we're really interested in here. That's the point of the eye tracking work. And I'm very new to this world. We've just done a couple studies in eye tracking, so this was a really good fusion of some of the work that the team here has been developing and some of the eye tracking techniques that we're working on. There are a lot of different ways of visualizing. I'm just listing a few here. So certainly we have this, being out in real world is an ideal context, but of course, you can't go and put up a number of these windmills or solar panels and then take them down and then put them in a different configuration and then do this over and over again. It just takes too much time and energy and effort, and also it would change people's perception because you can't randomize the order of any one of those things in a place. So VR offers that opportunity to do that. Augmented reality, the same. And in virtual reality, we can include all different kinds of 3D models to point clouds and things like photosphere images. And what we're going to focus on here for this study was a point cloud and photosphere and the real world. The photosphere data is still in process, so I'm not going to show you those data, but I will do the comparison between the point cloud and our real world. The question for this project really aimed at understanding the observational patterns and how they differ between these different mediums. Because the mediums can make a difference in what we perceive about the scene. And we're interested in a few different metrics to define what observations are. So things like semantic labeling of images, trees and grasses and that kind of stuff, but also just in general spatial patterns, and I'll get into some of those later in the results. So the benefits of this work that we sort of envision, one is the sort of the mechanistic understandings of how we can use eye tracking, particularly for really large areas. The vast majority of eye tracking studies are in more controlled, smaller spaces. There's certainly several work done in traveling around urban areas, but those still have quite a close envelope. This kind of environment is something where you can see for a quarter to half or even a kilometer. And thinking about how these sorts of impacts, like putting solar in a distance, would be understood. So that's the mechanism of understanding, evaluating those data. And then trying to see whether or not VR might really be a reasonable proxy for the way people observe these landscapes compared to the real world. And in navigation, as a side note, I'm interested in saying, can we actually help people understand their observational patterns? Could we train people better in making observations because we understand how each person might see and perceive the things around them? So let's dig into some of the methods here. The first is, this really was an experimental design. We had a number of different variables, so a basic demographic survey, we had ratings of the different scenes, we had a cognitive map, so you would draw what you remember in that space. And then we have the 3 different mediums that we're collecting along that. And then some of the dependent variables relate more to these metrics, the measures of spatial patterns in our design, as well as things like fixation rates. What are people looking at over longer periods of time? So 5 minutes for viewing a landscape, that's what we controlled in terms of the duration of time. We had to address some of these issues of sound in particular, because we know that sound can cause us to look. If all of a sudden there was a random sound to the right, most of you would turn briefly. We understand that's a case. That's really hard to control in an outdoor environment. This is a between subjects experiment because those of you that participated, we thank you very much for coming, but we wouldn't want to ask you to come again and again for 3 different mediums. So there's just a logistical reason behind that. And also, you would have exposure to these environments, which would create or require us to create some sort of randomized set of this. But we also didn't have everything ready by the summertime when we wanted to run the experiment. So between design is convenient logistically. We use the Tobii Eyeglasses 3 and the Vive Eye Pro. I'll give a little specifications of those later for our equipment. So the site is an area nearby. It is in a space where we can somewhat understand that there will not be too many people, but close enough for those of you to come visit, so we don't have to make you take a 2-hour trip and a 1-hour hike and otherwise to control the entire outdoor space. There was a really nice envelope of trees around us to sort of minimize potential for looking too far off with motion that might happen from, say, urban kinds of contexts or areas. There were a number of different distinct elements, so buildings and trees and vegetation and pathways. And so it created a nice sort of control space for us to work with. We conducted convenient sampling, as those of you know. It would be great to do a random sample, but those are super hard to get. There was actually quite a variety of folks because we also had a number of staff members come, people of different age groups, educational backgrounds. And we had 3 different ways of this. So the outdoor environment in the summer, the point cloud was earlier in fall, and then we started the photosphere and we're continuing some of those data collection now. A little bit into constructing the VR environment, and particularly the point cloud. So this is something that Lara and Ulrike had worked with before in collecting terrestrial LiDAR scanning. So this is a device that sort of spins around, shoots out a bunch of lasers, and then when you get certain reflectance back, it tells you how far away a particular thing is. At the same time, you have a camera that's registering a color for that particular point. So our brain is just interpreting that that thing is a tree, but really it's just a number of X, Y, Z points with a color value in space. So this is sort of the variation that you get from real world and left to a representation of that point cloud. The challenge with some of the point cloud, particularly as you go farther away, the number of lasers that you have to sample the points is reduced. And so you can use other data to augment that, in this case the Swiss topo, to add additional data into the existing frame of reference, as well as to sort of fill in the trees in our particular case. So these are the data sets that were used to construct the point cloud data. These were then imported into Unity, and I'm skipping over a lot of technical work to make that happen. And so the models, in essence, create different sections of all these point clouds that then get loaded. They're very large models to produce, and the gaming engine can work quite well with them. And then we had a Vive Eye Pro that my team has been developing software for eye tracking for a couple years to register when anybody looks at a point or a surface, it registers where that is in XYZ space relative to the user. So here's an example of the point cloud. We had people stay in the same location, but this just gives you some context of the quality and representation or limits and challenges to it. The loading that you'll get there is just an artifact as this video is being taken, but generally loading was all done before people went in, so you wouldn't see that or be distracted. And then here's a stitch of a panorama of photos that were taken at the same season. Okay, so into the procedures now. Procedures followed essentially the same thing with some variations. Basically, we had the social demographics data up front. And then if you were in the outdoor environment, like we have here, after the survey, then you got your earbuds for white noise to control the sound. We have a hat to control the solar exposure because too much infrared can affect the recording of your pupils and where they're going. And so that's why we have these different covers to work with that. And then also a device that records, the Tobii device that records eye tracking and a video simultaneously. So then we covered people's faces with a sheet and we had a walk. It was about 6 minutes. So this way they wouldn't have additional time and exposure to this environment, because that could affect the spatial cognition and things that they might be interested in. And we walked them straight up to this platform, and then basically restated the procedures again, took the blanket off, and then I stood behind them and flagged things. For instance, if there were insects like dragonflies or butterflies, and if there were birds, or if I saw a car moving or something else and people seemed to look that way, then I would flag that. Those are data that we'll go back and really work in and clean more later, but it's part of the variation we're considering within the data now. And then afterwards, we walk back and finish a final questionnaire. So the lab environment was essentially the same, other than we just had to calibrate the eye tracking itself in the lab. So a little bit quicker towards the end, but the same thing for those of you that had the lab. It was like dancing with you with the cable when you were spinning around. I would often have to take the cable and move it over so you didn't get caught. So it always kept it exciting for the moderator. So usually in the data analysis, I include that in the methods, but I have a separate piece here because I think it's really interesting data to work with, especially if you haven't been exposed to it. So the in situ environment, what we had was this Tobii eye tracker, and what it gives us are a range of different data. The one I'm going to focus on here is primarily the XY location that you are looking at in a scene. So while the video is recording, simultaneously it has all the timestamps at 100 megahertz of every point that you are observing. So that's a gaze point. That's represented in the red dot here. So we have all these data, and now we need to stitch together some sort of panorama so we know the entire 360 environment. So we used PT GUI for that. Adobe Photoshop actually does a lot of more warping with the image, so it doesn't have the same sort of horizon plane, and you can't control how well that image is stitched together. So PT GUI is some really nice software for that. In the future, we just take a 3D photosphere picture as well. So the third phase of this is now how do we get the scene data from the Tobii into the panorama? And that's where we use some AI I'll talk a little bit about on the next slide. And then the final bit is how do we take this vast amount of data from two different sources that have different sampling rates. And so we had to upsample some of those data and do some interpolations between those. So the AI piece is really quite interesting. We did not intend to utilize this, but it seemed to work quite well. And the reason is that the Tobii software that's provided to us tries to limit your scene that you have into another scene, and you have to go through every picture in a panorama and code all that, and it becomes manually extremely intensive and takes a lot of time. And as much as I'd love to be here for 6 more months, that's not what I wanted to do. So we use an AI technique. And essentially what it does is takes a scene, finds key points, usually hundreds or thousands, where there are similarities between the scene and where that might fit best in the panorama. And then it allows us to then transform those data. So here we have like 4 gaze points within one frame of the video. And now we can take a coordinate that was in the original scene and transpose that onto the projection of the panorama. So we could do that for the hundreds and thousands of data points that we have quite quickly, actually. So for about 20-some participants, this took 2 hours to render the entire data set. Usually you get a lot of warping, like what you see on the right. I just kept the left for illustrative purposes. So the data are still not done. It's quite complex because we have a flat image, but we also have to manage the interpolation of the data and the projection of those data onto a 3D surface. So the data themselves look a little bit like what you see on the left. They're kind of a bit messy, and we miss frequencies. If we turn too fast or our eye moves too fast, it might not be caught entirely. So we wanted to make sure that we could create some sort of similarity between all these devices, and that's what we're seeing kind of in the middle, is cleaning that. And the projection is taking something like the panorama, which is a cylindrical projection, but we need to put that into a 3D projection, so we understand where the X, Y, and Z values are located. So that was part of this whole underlying process of converting from 2 to 3D. For those who haven't seen eye tracking, this is just a little hint at what you might look at. So each of those boxes in purple is representing the millisecond of a gaze. And what we try to do then is look at these different sections. You can kind of see there are clusters, but how do we assume what those clusters are? How do we qualify those clusters? And then what you're seeing with these different lines are places where our eye moves quickly and so fast and so far away that we consider that a saccadic movement. Basically, not enough time for our brain to do any perceptual work of what we're actually seeing. So these all had to be cleaned, and once that was done, now we can start our results. So these are the number of data we have. We started with 26 participants in each. We ended up having 25 good sets of data that we could work with. It just happened to be that we had that many in both of these different experiments. And there, you can tell the frequency rate because the point cloud data had about half of what the real world happens. And the reason for this is the rendering speed and the frequency rate of the VR headset, because the point cloud was quite heavy and because there are limitations of hardware. So we're automatically dealing with a different set of data. This is why normalizing these is important. So we resampled those points. These are the interpolation points. And we look at places where there is overlap in some sort of projection space that we can analyze. And then we filter those data for the saccadic movements. It's quite interesting here that there's a lot more saccadic movement in the outdoor environment than there was in the point cloud, based on the way that we analyze the data. So here's the first take of an in situ environment. And what we're looking at is the proportional density of the angular velocity. So this is how fast and to what degree I am looking. So this is a high angle velocity, this is a smaller angle velocity. And we looked at those data between point cloud and in situ, and you can see there are some differences. We'll get into some of the reasons why in the discussion. We haven't ran any statistical significant tests, so I'm not going to give you any of those results, t-tests and otherwise, but you can see at least there's some trending differences between those. These are fixation rates that differ between the real world in situ and the point cloud experience. This is in milliseconds. And so what we're seeing is about an average of a half a second different per fixation, which is relatively substantial. But you'll also notice there's much higher variation in the point cloud. So people have longer fixations and shorter fixations within that point cloud. And the outdoor environment is more consistent, the amount of time that individuals were spending looking at the space. This is the vertical orientation to how we're looking at data. So 90 degrees is my horizontal plane. And the point cloud, people seem to look up a little bit more than in the real world environment. Again, statistical tests to come, but you can see there are some trending differences between those. This is the horizontal bearing overlaid onto the full panorama. So on the left, we have our 0 pixel to 7,000 some odd pixels that were then transformed to 0 degree bearing all the way to 360 degree bearing. So you can imagine the full thing wrapped around you. And the data, the proportional density you're seeing here is representing where people looked. This isn't up or down, this is just the orientation of my view. And you can see there are some differences between the point cloud and the real world. So in the real world, we tended to look more towards the water feature. And in the point cloud, we see some variation more towards the path. There's some other things back there. But there's something happening. We don't yet know what, but we see these data, and it at least gives us a question of how similar are these and why are we seeing these artifacts. So when we combine the horizontal and vertical data, now we are able to have a slightly different picture. There are a number of ways of interpolating these. We use this 10 degree by 35 degree because it visually is nice to represent. And what we ended up doing is take all the fixations that existed in space over this 8-point-some-odd million different pixel spaces. And for those fixations, you create an interpolation, a surface, because usually our views are somewhat continuous. So this is using something called inverse distance weighting. And we just subtract the two for this visualization. So when we see the blue space, we're noting that there's actually a substantial greater fixation for the point cloud folks compared to the in situ. And the red is representing where the in situ folks looked more often than the point cloud. And there are some key differences between these. Generally, there are great similarities, but you can see there are a few distinct differences. So this is sort of the fixation data and the patterns of fixation data. And now we're also interested, quite simply, what does the semantics tell us about this? There are also a number of ways to qualify this. This really is a first pass. We could do this in a number of different techniques to analyze the semantics. So here we have basically an overlay color for different types of features. So the tree line, the grasses, we have the platform and the dock, and then some of the buildings, which are a little tricky to see, I think, on the coloration back there in the blues. And we just said, okay, how many fixations fall within these boundaries based on the two different types? In general, there are similarities, but the folks that were in the real world looked at that pond and the near area far more than the folks in the point cloud. And for whatever reason, the point cloud folks tend to look a lot more at the tree line than the in situ. So there are some general differences that exist in the space, which might have us wondering, well, what happens to scenery management and these other sorts of things? Okay, so those are the results that we have right now. We're going to continue processing through these data. There are a lot of data and a lot of interesting ways that we can work with these. I gave my little homage to the flag there. I should tell you, when you download a Swiss flag, they always put it in a rectangle. Is that normal? It's just disastrous. People need to know their flags. Anyway, so discussion plus more questions, okay? So in the discussion piece, just to carry back the primary question, do observational patterns differ between the in situ real world and, in this case, the point cloud was the only one that we analyzed for this particular presentation? And what kinds of patterns are we seeing based on those fixation rates, their horizontal and vertical, and the semantic differences? And so you just saw some of those things. The key takeaway here is that there's certainly differences in horizontal and vertical. The extent to which those are statistically significant are to be determined, but the trends are there. We're also seeing differences in the XY patterns. So the pond and the water seems to be something that people look at in situ a lot more than in the point cloud. And then in the semantic, we have some other differences. So those are the sort of takeaway summaries where we're seeing things that are distinct between the different medium. And for the apéro, we're going to sort of start asking, well, why? And really, does this matter at all? So I've come up with 4 different concepts right now that I think could work to help explain this. I'm sure there are buzzings in your head. One of these is movement, particularly in the outdoor versus the point cloud. The other is if there are any sorts of distraction pieces. So movement can create distraction, but movement can also be a point of intrigue, right? Am I following a bird in the sky? Am I looking at that person walking? We didn't have that many people, but it could have had an effect. Am I watching the butterfly flip from one flower to another? What are all those that we could include? We can come back later and remove those data because we have them flagged and we have video to see some of those things. But the video is not necessarily clear enough for things like butterflies in any sort of distance. So this is why the flagging is important. So we can work to remove those data and see if we take out some of the motion, but you can't take it all because every single participant had some amount of wind. There's always some movement. The distractions can also be a result of that and other things. right? So there are smells that are going on out there as well. I'm feeling boards beneath me. That's very different than a controlled space. Also, just being out in another space that's new has a novelty effect in the real world that may not transfer to the same thing in a lab experiment. We need to dig through some literature to figure that one out. The detail is another piece. So afterwards, we have the VR headset here, so folks are welcome to come over and try it on and see the point cloud as well as the photosphere if you're interested. The point cloud had some detail differences. As you may remember a little bit from the water, it looked like there were some empty spaces within that, as well as the board itself and how things render. We noticed some people suggested, I can't quite see, I think that's a building in the distance. And that made us think about how much the point cloud can affect people's perception, even though that is a super highly realistic, high fidelity environment. And then data cleaning, when we think about the interpolation, when we think about the movement and how we assess the data, what we include as a fixation or not can also play a role in some of these data. So we're going to be processing these more and see if some of these preliminary results hold true. So future questions on this work. What role might demographics play? So we have the spatial cognition, right? These sketches that people produced, as well as ratings. So what kind of outcomes could we see between those different experiences as well? And then do the observational patterns hold true for the photosphere, right? The 3D image. Are we seeing something more towards the in situ because it's a photograph that might look more like the real environment than the point cloud? Or is it more towards the point cloud because it's visual? Or is it somewhere in between? Does the duration of exposure, this would be another study that I don't have time to run, but we had you in for 5 minutes. I cannot tell you how many times, around 2.5 minutes, I heard this. It's like there was a state of time that it took for everybody just to like, okay, I'm away from the rest of my world and here I am now. So I'd be curious to know if we had you in for 10 minutes, would those observation patterns differ? And can we observe these data through some sort of spatial temporal time to see, did fixation rate or the angular velocity change from the first minute to that third minute? Oh, sorry, I missed the second question because I'm trying to do this mostly from memory. So the second one was about the meaningful difference. I mentioned the point cloud, whether it's hybrid or compared to in situ or real world. But the second point actually was the meaningful differences in memory and preference. So that's about the rating, which I had mentioned. And then the last one is things like motion. So we could actually take a 3D camera, record a video, and then have people look at the video in the same space as things are moving to understand if there are differences in that as well. So there are a lot of ways that we could analyze and think about these type of data. Video a little bit tricky if we're trying to do these large scenario changes, but with a lot of AI modifications, we could think about scenario planning with motion and video in a higher fidelity photo-like environment. That's it. I think hopefully we're pretty good on time, and I'll be happy to take any questions.
Yeah, Brent, thank you very much for this super interesting topic and talk. It is impressive to see how much you guys achieved during this short time here. So it would be interesting to see what you achieve when you stay a little bit longer. Maybe there is the chance to come back. You never know.
Great.
Brent, thank you again for being here. Thank you for the talk. And yeah, I would like to invite you for the apéro, and thank you for being here for the last talk in this semester. And we are looking forward to the talks in the next semester. Thank you for being here.
Thank you. Yeah.